All right. So first I want to just review some ideas of related rates and implicit differentiation. The idea is that we're going to have variables that represent functions. They depend on the independent variable. So for example, in this first problem, which is an example of a related rates problem, so let me write that down. We have three variables. So I have my volume, my radius, and my height, because this happens to be the volume of a cylinder with a circle. So I've got a radius, I've got a height, and the cylinder has a volume. So those three variables, volume, radius, and height, they're all functions of time. They're all changing. And so when I think about this, I've got on the left-hand side volume, which is a function of time, and on the right I have this function of time that's formed from r and h. I can take a derivative of both sides, and the derivatives must be equal. This is the idea of related rates. So I have my formula for my derivatives, and on the left, if I'm taking a derivative of volume, I get the rate of change for the volume, so dv dt. On the right-hand side, I have pi, which is a constant, and then I have multiplied r squared times h, and so that's a product. When I take the derivative of that, I'm going to take the derivative of r squared, which is 2r, but because r is a function of time, the chain rule says I need to multiply by the derivative of my radius, and then times my h. So here's the derivative of the first times the second, and then we're going to add the pi r squared gets left alone. Sorry, we've already done the pi. I've got the r squared times the derivative of the height, which is the rate of change of height. And so here I've got the first times the derivative of the second. That's my product rule. This gives me a formula, or sorry, an equation. So if I multiply this all out, I get the rate of change of volume is equal to 2 pi times r times the rate of change of radius times the height, plus pi r squared times the derivative of, or the rate of change of the height. And so this is a related rates equation because it's an equation that relates these three rates: the rate of change of volume, the rate of change of radius, and the rate of change of height. I can solve for any one of those rates. So for example, if I were to solve for dh dt, the rate of change of my height, I'll need to move this term to the other side by subtracting, and then I'll divide by pi r squared. In this formula, where I've solved and isolated for the rate of change of height, once I know the rate of change of volume, the rate of change of radius, as well as the values for the radius and the height, I completely know the rate of change of my height. The second example is an example of implicit differentiation. This time I've got an independent variable x, and well, I have two variables, x and y. And I'm thinking about the graph of that equation in the plane. So we're going to think about y as my dependent variable and x as my independent variable, making this an example of implicit differentiation. We think of x as our independent variable and y as our dependent variable. And because it's dependent, we think of it as an implicit function. Now, by virtue of thinking of it as an implicit function, I can imagine that there's a function and calculate derivatives of both sides of this equation, just like I did for related rates, and I can solve for dy dx. So let's start by writing down the related rates equation. If I take the derivative, and this time x is my independent variable, so it's d dx of my function x squared plus y squared all squared. That's equal to the rate of change, or derivative, of 25. And I'll go through the process now of finding the derivative. On this left-hand side, I've got a quantity, let's call that u, raised to the second power. When I take a derivative of u squared, because my independent variable is x, excuse me, the chain rule will apply. And so this left-hand side is going to be the derivative of u squared, which is 2u, times the derivative of u with respect to x. And for this problem, that's going to be 2 times x, I copied that wrong, didn't I? X squared minus y squared, there's 2u, times the derivative of u. The derivative of x squared is 2x. The derivative of y squared, y we think of as a function, so it's 2y, and the chain rule says times dy dx. So let's fix that earlier bit. I need to change that to a minus, so we have the right problem. That's the derivative of the left-hand side. And, oops, there's another mistake. I was taking a derivative with respect to x. The derivative with respect to x is 0, because x was my independent variable. This is my related rates equation, and I can solve for my rate of change, my derivative dy dx. Well, this equation is set up so that it's a product equals 0, and if I'm solving for dy dx, so long as I have this x squared minus y squared is not equal to 0, I must have 2x minus 2y times dy dx, 2x minus 2y times the derivative. That has to be 0. And I can finish solving by subtracting 2x and divide by negative 2y. The negative 2 cancels, and I get x over y. This is my formula for my derivative using implicit differentiation. I can use that formula to find the slope at any point on the graph. I need to know x and y. With implicit differentiation, we're going to do two big examples of calculations using implicit differentiation. This first example is to look at a different way of finding the quotient rule. When we first looked at the definition of the derivative as the limit as h goes to 0, finding the quotient rule was really tricky. And what we're going to do is we're going to find a different way of finding the quotient rule. We'll use implicit differentiation. So if I start with the original equation, y equals a quotient, so the top or high is u and the bottom denominator is v, I can cross multiply and get an equivalent equation that the denominator low times y equals high. And here I have three dependent variables. So u, v, and y are all functions. We think of them as all being dependent variables, and x is my independent variable. Well, that means I could take a derivative of both sides of the equation, take the derivative with respect to x of the product, and that has to equal the derivative with respect to x of u. And using the product rule, I have last d first plus first d last on the left. That has to equal the derivative of u on the right. And our goal is to solve for dy dx. So we subtract y dv dx and divide by v. And what do we get? We get the derivative of y is the derivative of u, so du dx minus, let's do y times dv dx, and then we'll divide by v. And we're going to make a substitution that everywhere we see y, it's really u over v. So we get the derivative of the top minus high over low dv dx, all divided by v. And so this is one way of writing the quotient rule. But to make it look like what we're used to, I want to clear away this denominator. And so I'm going to multiply both top and bottom by v and distribute to both terms. And what do we end up with? We end up with v times du dx, that's low d high, minus u, the v's cancel, times dv dx, that's high d low, over v squared. And this is the quotient rule. So the quotient rule can be thought of as a consequence of implicit differentiation. Our second big example of using implicit differentiation to find something important is that we're going to find the derivative of the logarithm. Now the logarithm is the inverse function of an exponential, so we start with our basic facts. We know how to find the derivative of e to the x. The derivative of e to the x is e to the x. If I use the chain rule and I have anything else, so some other function other than just x, e to the x, if I have e to the u, my derivative is e to the u, chain rule, times du dx. So that's where we're coming from. Our inverse equation, if I thought about the logarithm, this is the inverse function. We don't know the logarithm's derivative yet. So we're going to find that using implicit differentiation. We start with our equation, y equals ln x, and we're going to find its inverse equation. So just a reminder where this comes from. If I have y equals the natural log of x, and I want to isolate x, I'm going to use the exponential, so it's e to the y equals e to the natural log of x. And the exponential logarithm, those are inverse functions, and so they cancel and I get x. And that's where my inverse equation comes from. Well, this is an implicit function. Y is an implicit function of x. So we can use implicit differentiation. The derivative of x has to be equal to the derivative of e to the y. Well, the derivative of x is 1. The derivative of e to the y by the chain rule is e to the y times dy dx. I can now solve for the rate of change, dy dx. And what do I get? Dy dx is 1 over e to the y. What we'll do is we will use our original equation, e to the y is equal to x, and I've just discovered a new derivative rule. The logarithm's derivative is 1 over x. That is, logarithm's prime function is 1 over x. Every time we have a derivative rule for a function, the chain rule lets us think about what happens if I have any other expression inside. The logarithm of anything is going to be 1 over that function times the derivative of what's in the logarithm. And I especially like this u prime over u. I'm going to look at the logarithm, what's inside, and the derivative is u prime over u. I should have had an example here, so let's do one. If I wanted to do a derivative of x to the 4th, sorry, that's not the example I wanted. I meant to say the natural logarithm of x to the 4th. Here I'm thinking of my u is this function x to the 4th. Well, the rule of derivatives say it's u prime, that's 4x cubed, over u, that's x to the fourth. 3 of the x's cancel, and I get 4 with 1x left in the denominator. The derivative of the natural log of x to the fourth is 4 over x. Alright, cool. We've sort of skipped over something. The logarithm has a domain, and the domain for the logarithm is that whatever the input function is has to be positive. So in this example we just did, x to the fourth is always positive except for x equals 0, so everything we've written is true. But if I use the logarithm of x, that x can only be positive, and so this rule for differentiation is only valid for x is greater than 0. Well, someone clever, I don't know who it is, hundreds of years ago, realized that I could do the natural log of negative x. And what this does is I'm now thinking of my u, it's negative x, and that means negative x is greater than 0, so x happens to be less than 0. When I calculate the derivative using the chain rule, I get 1 over u du dx. The negative signs cancel, and I get 1 over x. It kind of blows my mind that I have two different functions. The natural log of x gives me 1 over x for x is greater than 0. The natural log of minus x gives me a derivative 1 over x for x is less than 0. Well, I want to put those two together, and the way that I do that is through the absolute value, because the absolute value is x when x is positive, and it's minus x when x is negative. Which means if I have the natural log of the absolute value of x, this domain is both the left and the right side, and so I get 1 over x. The chain rule for that is if I have the absolute value of u inside the logarithm, its derivative is u prime over u, and there's no domain questions. If I don't have those absolute values, technically it's only the derivative when the input function is positive, and that gets a little messy. Alright, it's your turn to practice. So I have two columns. Notice the only difference between the left and the right is on the left I don't have absolute values, and on the right I do. And the thing that you need to know is that the two formulas are going to be the same for these two functions for their derivatives. The only difference is going to be their domains. And so I want you to focus just on finding the derivatives as formulas first, and then we'll talk about the domain in a little bit. Okay, so go ahead and pause the video and calculate the derivatives, and in a few moments after you've done your calculation, resume the video and see how you did. First, let's talk about the top row. In both of these examples, my u is 3x plus 1. So when I use the chain rule, the derivative of the natural log of u is 1 over u times the derivative of u. And so the derivative of u here is just the number 3. And so I get this formula. My derivative of the natural log of 3x plus 1 is 3 over 3x plus 1. Notice on the top, this is u prime. On the bottom is u. This is why I like the way of thinking about it is it's always going to be u prime over u. And the same derivative on the second problem. The difference between these two is the domain. So for the problem on the left, because the logarithm requires its input to be positive, this domain is where 3x plus 1 is greater than 0. If I were to solve for x, subtract 1 and then divide by 3, I get x is greater than negative 1/3. So this function on the left, the derivative is 3 over 3x plus 1, but only for x greater than negative 1/3. On the right, because it's the natural logarithm of the absolute value is always going to be greater than or equal to 0. So my domain for this problem is everywhere 3x plus 1 is not equal 0. In other words, x is not equal negative 1/3. just a single point. And notice that's the discontinuity point for the derivative. Okay, so if you haven't figured out the second problem, again, follow the pattern we just illustrated and see if you can find those derivatives. Okay, this time my u for this problem, the input of the logarithm is x squared plus 3x, and that's all I need to be able to find the derivative. It's going to be u prime, which is 2x plus 3 over u. And whether or not the absolute value is there, I get the same formula. The difference is the domain. So if I want to know when this is greater than or equal to 0, I need to do sign analysis. And the way I do sign analysis is I factor, so it's x times x plus 3, and I can think about where those are 0. So x equals 0 and x equals negative 3. Right, so these are my values for x, and this is my value for u. That's sloppy. And I can now pick values for x and decide the sign. So for example, if I pick a number like 1, I get 1 times 4, that's positive. If I pick a value between like negative 1, I get negative 1 times 2, that's negative. And if I pick a number less than negative 3, like negative 4, I get negative 4 times negative 1, that's plus. And so my domain is going to be the intervals less than negative 3 and greater than 0. So let's see, my domain for this problem is the interval negative infinity to negative 3 as well as 0 to infinity. If I have the absolute value, then this spot where x squared minus plus 3x is negative is also included. So for this second problem where the absolute value is there, I actually can have my domain is everything except negative 3 and 0. So we get this extra interval in the middle. But the cool thing is the derivative formula is the same. The absolute value allows me to get a bigger domain. Next, what we want to talk about is the properties of logarithms, how they help us with differentiation. We've discovered that the derivative rules for addition, or the sum rule, is really nice. We just take derivatives of each piece. But when a product or a quotient is involved, it's a mess. We have to use the product rule or the quotient rule. Logarithms have this nice property that if I'm going to calculate the u prime, or the derivative of what's inside, if I start and it's the logarithm of a product, I would have to use the product rule. But because of the properties of logarithms, I can rewrite it as a sum of two different logarithms. Each factor is in the logarithm, and I can then do the derivative of each term separately, and that's going to be easy. Similarly for quotient, instead of doing a quotient rule, I can use the quotient property of logarithms and break it so that it's the logarithm of the numerator minus the logarithm of the denominator. And even further, if there's a power, I can bring the power out. So that helps me avoid an extra step of the chain rule. Now, we've learned that to get the domain as big as possible, I need absolute values. The nice thing is that absolute value works really well with factors. So if I have something inside of an absolute value, every factor gets its own absolute value. And so it works for quotients, and it even works for powers as long as u to the power is defined. So here's an example of what we're going to do. If I were to calculate the derivative of the natural log of the absolute value of this product, and I didn't know about the properties of logarithms, I would write down and get started by saying that my derivative is 1 over that denominator, x squared times 3x plus 1, and then I would have to multiply by the derivative of x squared times 3x plus 1. And that would be true, but at this step I would have to use the product rule. And sometimes, this one's not so bad, sometimes that's not very desirable. What the rule for using these properties is if I think about each term, each factor. So let's see, if I go back and look at this formula, I have a factor of x squared and a factor of 3x plus 1 inside. And so each factor gets its own logarithm. So let's label them this way. So the logarithm of x squared, that power 2 that used to be here, has been brought out front. And the second factor, the 3x plus 1, gets its own logarithm. And now, this doesn't involve any product rule. I've got, for the derivative of 2 natural log of x is 2, there's the constant multiple, times 1 over x. And then the second term is plus, and now it's the logarithm of the absolute value of 3x plus 1. So it's 1 over x, 3x plus 1, and put the derivative on the top. And that's my value. It's 2 over x plus 3 over 3x plus 1. And that's a lot nicer than having to use the product rule. So on the next slide, what I want you to do is try it out. So we have the logarithm of a product. And in order to do this, you really need to focus on what are the factors. And a lot of students make the mistake of thinking that this is 4x to the third, but in fact it's a factor of 4, a factor of x cubed, a factor of 3x minus 1 to the minus 3 power, and a factor of e to the 2x plus 3 to the 4th power. Those are all of my factors. So what we're going to do is I want you to first expand it. So what you're going to leave the d dx and expand the logarithm using the properties of logarithms and absolute values and pull the exponents out. And then calculate the actual derivative. So again, take some time, work it out, and then resume the video. Okay, so check your work. I've only expanded so far. That's why I need to take the derivative. Notice each of our factors, 4, I get the natural log of 4, the natural log of x cubed, 3 came out front, the natural log of 3x minus 1 to the power negative 3, so I get this negative power brought in front, and e to the 2x plus 3 raised to the 4th power, and the power 4 is brought to the front. I'm now ready to take the derivatives. If you didn't work through that or need to check your work, again, pause the video, calculate these derivatives, and then resume and see how you did. Well, here we go. So the natural log of 4 is a constant. There's no variable dependence. So its derivative is 0. Constant multiple 3 times 1 over x. Constant multiple of negative 3 times 1 over u times du dx. Plus 4, that's my constant multiple, 1 over e to the 2x plus 3 times the derivative of e to the 2x plus 3. And then I've just simplified. All right. So far, so good. Awesome. All right, so here's one more. This will be our last one. I want you to take this logarithm of an absolute value. Remember, a quotient is a special form of multiplication. Everything in the denominator you could think of as having negative exponents, or you could use the quotient property of logarithms so that they get subtracted. Either way, our first step is we're going to expand before we take a derivative. So I want you to think about writing it as equal to, we have yet to take a derivative, expand that formula in terms of logarithms, and then take the derivative. Now here's the expanded version before I take the derivative. Each factor, and there are 4 factors here. There's a 3, there's an x squared, there's a 2x plus 1 to the minus 4 power, and there's a 5x minus 1 to a minus 3 power. And I've expanded the logarithm of that into 4 separate pieces, and now we're ready to take the derivative. So go ahead and finish that. Take the derivative. And here's what I get when I take the derivative. Constant has a derivative of 0, and each of the others, I've multiplied the coefficient in front, or the constant multiple, times the u prime in each case. So for example here, I had negative 4 times u prime is 2, that's where that negative 8 came from. Here it's negative 3 times 5, so that's the negative 15. My derivative is simply the sum of those 3 terms because I don't need to write the 0 plus. Alright, so that's the derivatives with logarithms.